Okay, quiz 13.2 on colligative properties. This quiz is, it looks like it's going to be pretty simple, but it's actually a deceptively complex and rigorous quiz. And part of the reason I didn't do a whole ton of examples in the lecture is because I knew we'd cover everything quite thoroughly with this quiz here today. So scrolling down, all questions on this quiz concern a solution of 12.5 milliliters of ethanol mixed with 36.3 milliliters of water. And so we have a mixture of two components. Here we have a table with their densities, their freezing points and boiling points, freezing point depression constants, boiling point elevation constants, and vapor pressures for the pure substances at 25 degrees Celsius. So a lot of data there that we may need to reference here. Let's move on to the first question. Calculate the mole fractions of water and ethanol in both the liquid and the vapor phase. So we're going to have to work out the numbers of moles of ethanol, the number of moles of water in order to get a mole fraction. And we were given volumes, which means that we're a couple of steps removed from what we want. We'll start with 12.5 milliliters of ethanol, 12.5 milliliters of ethanol. And volumes are really convenient to measure out when you have a liquid, but they're really not as helpful when you need to get into moles. We need grams, and so if we want to figure out the moles of ethanol, we'll look at that density, which is 1 milliliter is 0.7893 grams, 0.7893 grams. And that gives us a total of 9.866 grams of ethanol. And then we can, of course, take this one step further. The molar mass of ethanol is 46.07 grams. 46.07 grams is 1 mole. So how many moles of ethanol do we have? In the end, it's 0.2142 moles. Pardon me. We'll do the same thing for the water. That's 36.3 milliliters. 36.3 milliliters of water. And 1 milliliter of water is 0.997 grams. I'll often be lazy and just say it's 1 gram per milliliter. Technically, it's not quite. And so what we get is 36.19 grams of water, and then 18.015 grams is 1 mole, and that is 2.009 moles. And of course, you could have solved this in one step and not ever actually figured out the masses as an intermediate value, but I wrote the quiz, so I had some foresight, and I know that these numbers will be valuable to us later on. So we went ahead and calculated them right now. The total moles, and total is going to be the sum of those two, 2.223 moles. And now it's pretty straightforward to calculate the mole fractions of water and ethanol in the liquid phase. So the mole fraction of water is going to be 2.009 moles of water over the total of 2.223 moles. That is equal to 0.937. And the mole fraction of ethanol is going to be 0.2142 moles of ethanol over that total of 2.223 0.223 moles. And that is going to be 0.09636. And these two numbers add up to 1, at least within the correct number of sig figs. So these are our compositions in the liquid phase. About 10% ethanol, right? And about 90% water. Well, okay, 94% and hold up, that doesn't. 9037. 9037. I apologize. So that it is about 90% and 10%. 0.9037 and 0.09636. I apologize. I just was moving too fast and didn't read my notes here. Okay, so now that we know the compositions of the liquid phase, we can look at our vapor pressure lowering equation that says that the observed vapor pressure, P, and we'll say P for water, is going to equal the mole fraction for water times its pure vapor pressure. Okay, so the mole fraction for water is 0.9037, and the pure vapor pressure for water is 23.8 torr. 23.8 torr. And so this means that water is going to have a vapor pressure here of 21.51 torr. And we can do the same thing for ethanol. The pressure of the ETOH is going to equal its liquid mole fraction, which is 0.09636 times its pure substance vapor pressure, which is 44.6. And that's going to be 4.298 torr. 4.298 torr. And we can go ahead and combine these two to give us the total pressure, which is going to be 25.81 torr. 25.81 torr is the total vapor pressure of this solution. The water together with the ethanol. Well, now we can calculate my mole fraction of water in the gas phase. That's going to be the pressure of water over the total. That's 21.51 torr over 25.81 torr. And that's going to equal 0.833. And we can do the same thing for the ethanol. Oops. The mole fraction for the ethanol in the gas phase is going to be the partial pressure of ethanol over the total pressure. That's 4.298 torr over 25.81 torr. And that's going to equal 0.167. And so if we compare these mole fractions in the liquid phase versus the vapor phase, you can see that the ethanol has been enriched. It's almost double, actually, the amount of ethanol that you started with. Oh, maybe another 2/3, not quite double. And this is why distillation works. Right? Then you can collect these vapors, recondense them, and do this whole thing a second time, or a third time, or a fourth time. And if you get really good at it, you can bottle your product and sell it for a good profit. So this is how distillation works, how we're able to purify one substance over the other. If you run this distillation long enough, then what's left behind will actually become enriched in water, because the ethanol is vaporizing more rapidly. So you can actually purify both ways. You can get water more pure by evaporating away the ethanol and keeping the water behind. And you can get ethanol more pure by evaporating it away and then collecting those vapors. All right. Now the next question, sorry, this was all just calculating the mole fraction of water and ethanol in both the liquid and the vapor phase. Question 2 says, because water is the majority component, freezing and boiling points will be determined in relation to water. In other words, we've got freezing and boiling temperatures here for both water and ethanol. And if you're going to be calculating freezing point depression values and boiling point elevation values, you'll get different answers depending on what you choose to use as the solvent and what you use as the solute. And like most things, it can get complicated in edge cases, but we've got 90% water here. Water is the majority component, and so we'll use that as our baseline. We'll consider ethanol to be the solute, which indeed it is, and calculate our freezing point and boiling point depression constants from there. So I'm actually going to leave these numbers up here. I'll just erase the bottom half. Okay. So I'm going to want to calculate, first of all, the molality of this solution. So the molality is going to be the moles of solute over the kilograms of solvent. Well, if ethanol is our solute, then that is 0.2142 moles. And water is our solvent. And we want it in kilograms. I told you this mass here would be useful. We have 36.19 grams of water, so that is 0.03619 kilograms. And this gives us a molality of 5.919 molal. A pretty high molality. Now we can calculate what is our delta TF, our freezing point depression constant. Our freezing point depression is going to be negative KF for water. That's 1.86 degrees Celsius per molal, times that molality of 5.919 molal. And we have a Van't Hoff factor of 1 in this case. Ethanol is a non-electrolyte, so we don't need to do anything more complicated at this point. So delta TF is going to end up being negative 11.0 degrees Celsius. And so TF is the normal freezing point of 0 minus 11. That's going to equal negative 11.0 degrees Celsius. This will freeze at a much lower temperature than normal. And then delta TB, that is going to equal our boiling point elevation constant for water, which is 0.512 degrees Celsius per molal, times that molality, 5.919 molal. And what I get is 3.03 degrees Celsius for the boiling point elevation. And that means that our new boiling point is going to be 103.03 degrees Celsius. Okay, now question 3. Sorry. Question 3, the mixture will have a final volume of 47.5 milliliters. So I'll just write this down over here. VF is equal to 47.5 milliliters. Let's calculate the density of the mixture. First we'll take our total mass, and that'll be the 9.866 grams of ethanol plus the 36.19 grams of water. That gives me a total mass of 46.06 grams. Density is just mass over volume, and so we'll divide that by our volume of 47.5 milliliters. We don't need to do any unit conversions. Grams per milliliter is an acceptable unit for density. A milliliter is equal to a cubic centimeter, so it's the same as the grams per cubic centimeter given above. And this is going to be equal to 0.970 grams per milliliter. 0.970 grams per milliliter. Now this may not seem all that surprising. It is a density that is intermediate between the water and the ethanol. But if you dig a little deeper, it's not like, it's not 90% of the way toward the water like you would expect. What happens when water and ethanol mix is that they actually contract in volume. If we go back to the original 12.5 milliliters plus 36.3 milliliters, sorry, I'm actually adding those up right now, that should be 48.8 milliliters of total volume. But 48.8 is not what we observe. We observe 47.5 milliliters. And I looked up true values. I looked at an actual density table for water ethanol mixtures. So this is what you would expect to observe in reality. The volume contracts a little bit, which is kind of cool. Basically, the ethanol water mixture is pulling particles closer together than either pure water or pure ethanol. Okay, and then lastly, how much osmotic pressure will this solution exhibit? Can get rid of the density stuff here. Remember, pi, our osmotic pressure, is equal to nRT over V. N is going to be 0.2142 moles. That's the number of moles of solute particles. Van't Hoff factor is just 1 because this is a non-electrolyte. R is our gas constant, 0.08206 liters atmospheres per mole Kelvin. And our temperature, I guess I technically didn't give you a temperature except that I referenced the pure substance's vapor pressures at 25 degrees Celsius. And that's what I intended, was 25 degrees Celsius. So this is going to be 298 Kelvin, 298 Kelvin. We'll divide that by the volume. 47.5 milliliters is going to be 0.0475 liters. And this gives us an osmotic pressure of 110 atmospheres, which I think is pretty impressive. These osmotic pressures can be really surprisingly high values. 110 atmospheres is quite a lot.